I'm going to talk to you today about how geometallurgy has evolved over the last 20 years. So we had three basic problems to resolve. We'll talk about that. Geomet objectives to develop a new technical field that we've all seen as common sense. There were different scales and different languages that we needed to bring together. How do we do that? This was my experience in the MIRA P843 project. Then there was like, how do we do data management? How do we get everything to fit together? And then when we got down to the really hard part was, how do we actually get the professional work cultures to change? Some final thoughts. Where are we going? Because there's actually a clear direction geometallurgy is taking to now that wasn't seen even 5 years ago. So these are the steps I'm going to go through in the next 19 minutes and 38 seconds. Yeah. All right. First problem. This is what used to really upset the capital investment the most. Here is our rate of achievement to design capacity. So let's say this is dotted line is 100% capacity, and the curves are the time. These are the quarters along the bottom. How long does it take to actually commission a mine and get it up to speed? And there were four groups. Group one got there fairly quickly. By the second quarter, they were producing essentially what they were planning to, but other groups were not. And some groups were actually really slow, and some didn't make it there at all. Now, this is fatal because the net present value of the deposit was absolutely dependent on how fast they could make money. And the money they make first is actually more valuable than the money they might make in 5 years' time. So this was a real problem. So here are some CapEx overruns. This is as far back as 2006. I'm sure there's some more updated information, but this really makes the point. In terms of CapEx for the feasibility of what we think is going to happen versus what actually happened, well, we got it wrong quite a few times. Like, can you get something 100% wrong and still call it engineering? That's an interesting question. So how did this happen? This is what and this was the third problem. Here is a grinding circuit somewhere south of the North Pole, planet Mars. Sorry, this one's on planet Mars, an unknown mine site. So we've got mill feed and you've got mill power, and this is over a 7-day time frame. The third plot on there was actually recovery, and they asked me to take that off, and it actually looked the same. This circuit was uncontrollable. So this is in operations. A mill is actually designed around a steady state, but that steady state average never seems to happen. So how do we actually hold things together? And geometallurgy was supposed to actually evolve the characterization technology to sort out these three basic problems. How can inherent variability in feed in most mining operations be better measured and quantified in order to improve process control, profitability, and sustainability during manufacturing? What measurements should we do? And at what scale and frequency? These are the questions that were posed 15 years ago. How effective is blending to control the average, and is it sensible? And what modifiers to grade and metal equivalent can be used or should be used to calculate the true economic value of the ore? So consider how mining can be like a modern manufacturing industry. So, yeah, what are our economic modifiers? What routine site-based measurements could be used? What links could be established between small-scale tests and the relatively expensive tests? And could we develop those tests? And what role can simulation and modeling play? So here was our starting point, and it was a lot of the people who've been in the mining game for several decades intuitively understood all of these things, and so we actually needed to actually make the tools and make the language to actually make them available to everyone. What we were looking at in terms of characterization was the idea between constrained mineralogy in sampling and a process engineering application. We're looking at a behavior response in an efficiency window. What we're saying here is, let's say we're looking at flotation. Does the flotation cell see different ore types? And if so, what are those ore types from the point of view of that flotation cell? So that was the paradigm shift. So this was an idea that Steve Walters came up with. In fact, a lot of these ideas have actually originated with Steve. He was remarkable in bringing together some really, really interesting ideas in a non-linear way and able then to communicate them, which could then be implemented. He came up with the idea was the rock was like the Rosetta Stone. The ore type that we're looking at, all groups are using the same piece of rock. The geologists, the mineral processors, the miners, we all touch the same piece of rock, but we are looking at it in a different way. So if we're looking cross-discipline, in a cross-discipline concept, how can we have a transfer point? It was actually the rock itself was the transfer point. And so we wanted to develop a sampling and testing strategy that of that rock that actually talked to all technical professionals who actually might use it downstream. So, and that led to a discussion about like, what is an ore type? What are the rules? How do we decide what's an ore type and what's not an ore type? Is it grade? Is it texture? Is it what? And if we're actually looking at multiple groups, how do we do that? And how do we populate that? And so there was a bit of discussion around that. Here's our technology integration pyramid, where up the top, we've got our really expensive tests like MLA and flotation tests, and down the bottom, we've got chemical assays and visual logging. So this is how things were, and there was the recognition that we needed to completely reinvent this whole thing. Down the bottom, we had lots and lots and lots of information, but it wasn't that useful. And all the information that really was useful was up the top and very expensive, and it was very hard to get in contextual. Could we develop links between the different levels that were more effective? And could we make them more accessible? Not only we needed cheaper tests, but we also needed them to be more useful. So that was an evolution. And so this is where all the small scale test drive came from. Then there was the question of scale. First thing I teach you in geomechanics, day one. The scale of your question really does dictate the scale of your characterization. So if you're looking like at, say, a pit face, and well, if you're looking at a scale of, say, 7 or 8 meters, you can start seeing joints. But if you're looking at a scale of 3 or 4 centimeters, you can't see joints, but now you can see individual mineral grains. Rip it out and put it under a microscope, you go finer again. So how do we get that mentality and then bring it into the geometallurgy space? So then we had the conversation about who were you, what were you, and what were you doing when you looked at the same piece of rock. So the macro scale texture, this was the blasting guys, 10 meters to 1 meter. The mineral processor guys were more mesotexture, a rock you could hold in your hand, say 50, 60 centimeters in size. But then the microtexture guys, these are the flotation guys, or the leaching guys. They were interested in particles that were very small. And so how do we get these groups to talk to each other in context of consistent characterization? So now we get into the geomet language. Each technical group had to leave its comfort zone. I saw this happen at the JKMRC back in the 2008, 2009. And it was remarkable. Comminution and flotation sat down with mineralogy and geology. And each group was absolutely convinced that they should rule the world and everyone else should listen. But each of us actually had to leave our comfort zone. And so how we saw the mining process had to evolve. How we did our test characterization, what for had to be looked at and reinvented. And then what did we do with the results? And could we actually cross-fertilize different areas with those same results? So it started out with comminution and geology. It came down to how the sciences themselves work. Comminution is very empirical, bang the rocks together and hope for the best. Whereas geology is more descriptive science, and they tend to measure things more often, but it was a very different paradigm. So geology saw things in terms of spatial definition, where something was in the deposit. And they were more concerned about how an ore formed or how it was held together. And they didn't care at all about how it might behave in a process plan. And they approached the ore in terms of mechanistic modeling and organic modeling. Process engineering saw things in terms of time, when an ore type was coming up the belt. from the stockpile? When were we going to look at it? And we also viewed the ore stream like a bulk material, behaving like a fluid as it passed through our pilot plant or our process plant. And comminution approached the ore in terms of empirical measurement. Both paradigms are refitted and merged, forming a completely new discipline that bared little resemblance to both parent disciplines and was a fundamentally different animal. So we had to go around this loop many times. First of all, it was the mesoscale texture. A group of geos looking at a core tray. What do we see through a hand lens? Versus what does a flotation cell see and how do we measure it? It's actually the same piece of rock, but how do we merge the two? This is actually one of Steve's slides, Steve Walder's. Geologist has a predisposition to describe rocks in terms of their genesis. What color it is, where it is, how it formed. The language is interpretive and often influenced by exploration. And Steve does like his poetry. The mineral processing guys, they saw it as a bulk feed material for a manufacturing process and should be described in terms of processing characteristics. The variety of relativity. Tell me what my feed size is relative to my starting point, not what the rock used to be. How will it perform now in these circumstances? I don't care how old it is. And so then we had different methods. Different methods were put together, wildly different methods. So the top left-hand corner, you have a big core scan map. It's about 1 kilometer of core, reached line as a core tray and different spectra. And all the way down to MLA data in the bottom right-hand corner. So we had very different pieces of information. How do we actually bring that together? Let me just skip through here. So we had our data measurements. So we're looking at very different data, and we had to somehow get them together. And so we could start classifying, were they trends, rankings, calibrations, or behaviors? And how do we get them into one data set? And this was actually more difficult than you might think. With the understanding that we're going to do some engineering design here that must honor the geology, but use it, and then that will then later be used for corporate decision making. We had different platforms. I'll skip through this for time. And texture. What's this strange beast called texture? And this was actually one of the parts that were really difficult to resolve because everyone had a different answer. So here is like a 10 millimeter block that was under the MLA. All minerals are looked at. And that's the chalcopyrite only. And that's what the mineral process guys normally get. What we really want to know is what's around each chalcopyrite. And so how do we actually get that? So from the perspective of mineral processing, what do we need to know? I'm going to skip past this for time. And so, yep, skip past that one too. Okay, so the conversation is culturally, is that we, instead of each group saying, do it our way, we're more important, it now comes to how do we evolve and work together? And if we can't do that, then you're not useful to me. So professional silos professionally had to actually be broken down. Groups had to be forced together, and it worked best when they actually had no choice. This was actually quite a difficult process. What started to happen, though, was technology. This is where we're going. So the idea of the remote operation and data center, and who has control, and how do we measure stuff, and how do we use that information? This is actually the future of mining. So conventional geometallurgy happened on the laboratory scale. We'll do our tests and we have a series of behaviors. But what we actually want to know is how it's going to operate in a mine site production. And the behaviors there are some kind of instrumentation measurement. So behaviors in a geomet lab scale have to talk to some kind of measurement in the plant with the new kit that's coming online, especially the hyperspectral stuff. So geometallurgy was all about the feed sample goes into a process. We're going to characterize the feed and the products and then work out what goes where and why. The instrumentation would then measure similar things as well, but the information is quite different. But we had to get that information to talk to each other. The evolution will go something like this, as happened over the last 50, 60 years. We started out with the intuition of geologists and mineral processing, doing conventional tests. There was a new technical language and a recognition for the need for the mining to evolve. Development of a series of small-scale tests started. There were several attempts to commercialize those tests. We started to see some inappropriate use of test data in block model development. Things that weren't additive were tried anyway. Then we had the mining crash that stopped all development in its tracks, and that was hilarious for anyone involved with that. What came out of that, what really did evolve, though, some much more intelligent experimental design to problem solve in the mining industry using conventional methods came. We worked a whole lot smarter. The geomet was a concept that was now more widely accepted. Instrumentation and spectral analysis linked to ore type has started to appear. When I characterize a rock now, I'm characterizing with all the conventional stuff. But in addition to XRD, XRF, I'm now looking at Raman spectroscopy and Fourier transform spectral analysis, as well as some kind of thumbprint. We're now looking at machine learning and AI that's handling large volumes of data. In the GTK system, we are building a digital twin for our pilot plant. A lot of data is being characterized and collected, and that's going to be put up against a geomet study. And a systems merging of block model, mine schedule, design, grade control operations, meta count reconciliation is starting to come together, and it'll be machine learning driven. All right, that's it. Thanks.